right, let's take a look at page 249, but also the graphs on page not 249, oh my gosh, 429 and 428. We're going to play our little matching game that we started yesterday, but we didn't have time to finish. So yesterday we were looking at slope fields, how they are a pictorial or a graph representation of the of the slope at any given point that you wanted to select. So if we're given a differential equation, aka a derivative equation, we can plug in a point into that derivative to get the slope, but when we're all said and done with these slope fields, they should resemble the antiderivative, okay, the graph or the equation you would get if you were to work backwards. So we're going to try to practice matching up the different slope field to either a differential equation or a solution, aka antiderivative. So on this first set of matching, we were given the derivative equation, and yesterday we worked backwards. Now we're going to try to match up the solution, aka the antiderivative that we discovered, with the appropriate graph on the other page. So you may have to flip back and forth. Maybe you can lay out both of them at the same time so you can see them. But when we worked backwards, let's see if we can think about what the different shapes of these graphs would look like, and then try to pick out the one that most resembles that shape on the other page. So we have 10 of them to go over. Maybe some of them might be easier than others, but as soon as we get rolling, it should start to get more easy for us because we are eliminating some different options. So if you take a look at all 10 equations on page 429, is there one or two of them that you can look at and you automatically know, I know what that graph looks like, or I know what that shape looks like for that particular equation? Can we narrow some down? What do you think, Joseph? Go ahead.
B is exponential.
Say it again.
B is exponential.
B is exponential. Okay, so you're looking at these graphs here. So looking at the shape of the graph, yesterday we practiced plotting a point and then drawing the solution curve. So for example, if you were to pick any point on B and follow the curve, follow the slopes, it would most likely resemble an exponential function. So let's go ahead and take a look at all of the antiderivatives that we found yesterday, okay, numbers 1 through 10. Of those 10, which one is exponential? You have a base to a power. 3, right? That's e to the x. So if you take a look at all of the slope fields, I think that's the only one that resembles that exponential path or curve. So then number 3 must match to the letter B slope field. Okay. Can we find another pair? Either looking at the slope field graphs, think about what type of function those are, or maybe looking at the equations, number 1 through 10, and thinking about what would that graph look like. We can go either way. Can we find another pair or possibly discuss some options? A is quadratic. Okay, so let's take a look at the graph. If you were to pick a point and follow the slopes, probably looks something like that. Are there any other quadratic looking ones on the graphs? F is another one. Yep, I'd say if you pick a point and follow it, you'd get that parabola shape. So that's another quadratic. And G, yep, but G is an upside down parabola. Yep. So it looks like we have 3 quadratic looking slope field graphs. So those should match up to 3 quadratic solutions, aka antiderivatives, that we found yesterday. So the quadratic ones look like 2, 7, and 8. can we narrow down which ones are which? G is, how'd you know G was 7?
Because it's upside down, so it has to be negative.
There you go. Notice how that quadratic term, the x squared term, is negative, so that would be an upside down parabola. That matches our graph from G. And A and F, they're upside parabolas, so they should be positive squared terms. But when you analyze them a little bit more closely, it looks like F has the minimum on the y-axis, where A had the minimum a little shifted to the left a little bit. So can we think about, let's see, our only other options were 2 and 8. Which one would produce a parabola on the y-axis? Which one would produce a parabola that was shifted a little bit?
F would be 8 because there's just no other term.
There's no other term, right? You have a x squared term, a regular parabola, and if you're adding some constant on the end, hopefully we remember our transformations, that's just moving a graph either up or down. So it's staying on that y-axis, it just depends how much you want to move it up or how much you want to move it down. Okay, that c value is going to vary. That's why we have all these different options of the solution curve. So that would narrow down number 2 to be A. Since we have that kind of extra variable term in there, that's shifting the graph in some capacity. All right, so we've narrowed it down. We have 4 of the 10. Can we start to think of or match up some other ones? C is cubic. Okay, so if we take a look at the graph of C, if you were to pick a point wherever you wanted and follow the slopes left and right, you would get that kind of curly S shape. And I think that's the only one of the graph we have. So if that's a cubic graph, let's match it up to our cubic antiderivative. Looks like that would be 9, right? 1/3 x cubed. All right. Can we identify any other type of graph? We're halfway there. J is linear. Pick a point wherever you want. Follow the slopes to the right, to the left. Doesn't matter which point you pick, you always get a line. All right, so our solution, aka antiderivative, should be linear. Of the ones we have left, looks like 4, 2x plus c. All right, we're down to 4. And if we do the easier ones first, that means they kind of get a little bit harder as we go. Maybe if we're getting stuck on looking at the graphs, maybe we can look at the equations to think about what those might look like graphically. H is quartic. Good. So quartic graphs kind of look like a W shape. And if you were to pick a point and follow the slopes left and right, it would start to look like that W. So our quartic antiderivative was 5. All right, so we've narrowed it down. We have the trig ones left and the natural log. And it doesn't surprise me that those are the ones that are left because usually those are the harder ones to pinpoint. If you take a look at your 3 graphs that are left, can we label any one of those? Can we match them up somehow? E is probably the natural log, right? Trig, sine and cosine graphs are waves, so it makes sense that D and I would represent those trig ones. So E would probably be that natural log graph. Okay, so we'll label that as a natural log. So let's talk about the differences then between D and I. Maybe we can relate that back to 1 and 6, the ones that are left. So we kind of have a 50-50 shot here, but what can we look for either in the equations or the graph to help make a connection? Yeah?
Number 6, the sign has a 2 in front of it, so we'd have the bigger waves.
It'd be a bigger wave. The amplitude was kind of stretched, okay? So if you take a look at D and I, which one seems to be the bigger wave? Probably D, all right? So there's your sine graph. So we'll label that as D. And then last but not least, number 1 would have to be I. So you can tell that this one would be cosine, because cosine graphically starts at 1, just like on the unit circle, it starts at 1. But since it's negative, that means it was flipped upside down. So notice how instead of starting up here and going up and then down, it now starts down at -1 and then goes up and then down. So it had that flip to it, that negative. Looks pretty good, guys. All right, so that was one way that we can match up a differential, aka derivative function, to any particular slope field. We're going to try another one. All right, so let's take a look at the next page. Okay, we have 431 and 430. Again, we have this matching going on that we're going to try. Notice how on page 431, though, these are not the derivative equations, okay, the differentials. These are the antiderivatives, what you would get if you were to work backwards. So we don't have to work backwards like we did yesterday. It's technically already done for us. What we need to try to think about is just at face value, if these are the antiderivatives, what would they look like in terms of a graph? All right, so maybe we can go through and jot some things down that we should probably be looking for. If you think about the equation y equals x, okay, that's linear, so we should probably have a slope field that resembles a line. We said x squared was quadratic, so we should be looking for that parabola. E to the x is exponential, so we should have that kind of quickly growing graph. Off the top of my head, I don't really know what 1 over x squared looks like, so maybe I'll just leave that blank for now. Cubic graph, you have that kind of curly S shape. Sine graph starts at 0, goes up and then down. Cosine graph starts at 1, goes down and then up. Do we know what a square root graph looks like? Kind of, yep. It starts at the origin and then it's kind of a half of a parabola on its side. All right, y equals 1. That's a horizontal line. What about tangent? This is a good one. We know sine and cosine are the waves. Tangent's a little different. Yeah? It's like a bunch of cubic ones in a row. So it's going to look like the cubic, but we have that repetitive periodic graph or periodic function all the way through. So just like a wave is periodic, it repeats itself, so does this tangent one. So it's a bunch of those cubic looking shapes. All right, so out of all those 10, we don't know one of them off the top of our heads. So I think that's a good process of elimination that we can use. I want you to take the time, now that I can identify what the graphs should look like, match them up to the slope fields that resemble that graph. Let's see, can we identify our linear slope field out of those 10 options? C, good. Can we identify the quadratic slope field? Number 2. A, looks good. What about the exponential slope field? F. 3 for 3? All right, let's skip 4 because we were a little iffy on that one. Can we identify the cubic slope field? H, I like it. All right, what about the sine slope field? Maybe we'll skip it and come back to it. What about the cosine slope field? What was that? E, how'd you know?
It starts at 1 and goes down.
There you go. So if you were to pick that point at 1, notice how that's a maximum, and it goes down and then up. Okay, that's kind of what's happening here. It starts at a maximum, goes down, and then up. So if you were to identify E for the cosine slope field, can we go back to the sine slope field? Most likely B. Okay, that's our other wave graph. All right, what about our square root slope field? J, right. The square root only shows up on the right-hand side of a graph, so it makes sense that the slope field would only be on that side as well. Can we identify our constant slope field? G. All right. What about our tangent slope field? I. So that must mean number 4 was D. Right. If you were to graph number 4, hopefully we realize we'd have a vertical asymptote at 0 because that would make the denominator 0. And you'd have these two kind of L-shaped graphs on either side. So notice how the graph of D, or the slope field of D, resembles that shape. Okay? How do we do? Pretty good. All right, so we officially have gone through all 4 criteria that should be expected of us for this section and on the AP test. So yesterday we graphed slope fields by hand, and we also plotted a point to draw a solution curve. Are we still good with that from yesterday? Okay. What about the matching from today? Can you match slope fields to either a derivative equation or a solution equation? I think we did fairly well. Okay. We're going to take a look at kind of 2 examples of how slope fields typically show up on an AP test. So we're going to take a look at a multiple choice type problem, and then we'll take a look at a free response. All right, so for the first one, we have a given slope field. So this is going to be kind of a matching activity for us. We're going to see of these different derivative equations which one would generate that slope field. And it's more of what I want to try to do is just more talk about it, like what's a thought process you can use or a process of elimination to help you go through and determine which one of those would generate this slope field. So when you take a look at this slope field, are there any slopes that kind of stand out to you, like we know exactly what the slopes are at specific points? All right, so at an x value of -1, notice how we always have a slope of 0. So maybe we'll just pick a point, maybe this one right here, and that point has the coordinate -1, 1. So let's go ahead and test that point, -1, 1. We know at that point the derivative, aka slope, is 0. So let's take that ordered pair and test it into the different slope or derivative equations. When you plug in -1 for x and when you plug in 1 for y, you should get 0. Did we get 0 for any of them? C and E, right. If you plug in -1 and 1 for the first one, you get -1. You plug it in for the second one, you get -2. Plug it in for the third, you get 0. Plug it in for the fourth, you get -2. And you only can plug in -1 for x in the last one because that's the only variable you have, and you get 0 for there. So at least we were able to eliminate 3 of the 5 just by testing that one point. But unfortunately, that one point is not enough for us to determine which one it is. So let's go ahead and try to move on to another point. Can you find another point on that slope curve that has, or slope field rather, that has a slope we should know, or that we know what it is exactly? Probably choosing another 0 slope is not going to work out for us. You could try it, but I'm pretty sure that these are going to result in 0 again. Can we test another point? 1, 1. Okay. Is that what you're going to say, Dan, or you're going to pick a different one?
Yes.
What were you? You were going to pick that one too? Okay. So what is the slope at that point? It looks like 1, okay, a 45-degree angle perhaps. So if we plug in 1 and we get out 1, our slope should be 1.
1, 1, I think. Never mind.
Is that 1? Well,
0, 1 as well.
maybe we'll probably, okay, so you think that one is 1?
Yeah.
Okay,
0, 1 is there.
let's try that one then. We'll do 0, 1. Alright, so we're only going to plug it into the 2 that we've narrowed it down to. If we plug in 0 and 1, we get 1. If we plug in 0 and 1, we still get 1. That one didn't help, right? Can we test another one? Pick another point. What if we tried that 1, 1 from before? Let's go back to that. We said the slope might not be 1, maybe it's about 2, a little steeper. If we plug in 1 and 1, and for C we'll get 2. If we plug in 1, and for the last one, we'll get 2 cubed, which is 8. So based off of that slope, does it look more like a slope of 2 or a slope of 8? Probably 2. 8 would be drastically steep. You go up 8 over 1. That's very steep. So with that testing point, we can mostly narrow it down to C. Okay? So sometimes, I don't want you to think about you always have to work backwards to figure out that antiderivative, because testing or working backwards from all of those may have taken us some time. If you're given kind of a matching activity, try to test different points to see if they match up. Okay, easy process of elimination. Let's try a free response type question. All right, so we have the derivative or differential equation x over y. On the axis below, sketch a slope field for the equation. Now, what's a little different for this one is notice how the derivative is a fraction, and whenever y is 0, you're going to have an undefined slope, right? So on your slope field, you can't really graph a slope at that point if it's undefined. So the y value of 0 happens on the x-axis. So there are not points at these spots, just to clarify. You have the rows above it that have 5 in each, and then you have the rows below the x-axis that have 5 in each. So can you guys take the time to go ahead and plot the slopes at those different points? You do not have to go on the x-axis. Maybe you'll start to see a pattern after a while. Maybe not. Maybe you want to do each one individually. Completely up to you. Remember, slopes of 0, 1, and -1 should be exact. All the other ones should be relatively close to what the slope actually is. How's your slope field look? Taking shape? All right, let's try part B. Sketch the solution curve that passes through the point 0, -1. So let's go to that point on the curve or on our slope field, and we'll plot it. And we're going to follow the slopes to the left and to the right. Okay, as you follow the slopes, your pencil should be parallel to the slopes. So maybe we'll go to the left first. As we go to the left, we're starting on a slope of 0, so it should be level. But then as we travel to the left, trying to be parallel with the slopes, looks like we're going to go down as we go to the left. And to the right, we're starting off with a slope of 0. But as we go to the right, following the path of the slopes, looks like we go down as well. Do you think you'd be able to draw that? Okay, let's try C. So now that we drew the solution curve at that point, 0, -1, they're asking us to find the particular solution. Okay, that antiderivative, the exact equation that would have that graph. So this is going to be the by hand or the calculus part. So let's go ahead and take a look at the derivative at the top. We want to go ahead and work backwards, aka integrate that derivative equation. How might you want to do that? Cross multiply. We got to separate those variables. Okay, so we're going to have the y's on one side and the x's on the other. Remember, just by doing that, you would have earned a point. It's a big first step. So now that the y's and x's are separate, we can work backwards from each side individually. We would have 1/2 y squared on the left and a 1/2 x squared, don't forget the plus c, on the right. That probably would have been worth 2 points. Okay, 1 for having the correct antiderivatives, and then another point for remembering the plus c. Do you think you'd be handling your own at this point by now? You could do that? Let's go ahead and solve for y. So we'll divide the 2 over, or sorry, divide the 1/2 over, aka multiply everything by 2. You don't have to write 2c. You can if you want to, but 2 times a constant is still a constant. And then get rid of the y. We're going to square root both sides. So we have that plus or minus out front. So there's the general antiderivative, the general solution, but it wants the particular, okay, the exact solution, the exact antiderivative that goes through this point. Okay, the exact equation of this curve that we drew. So how do you want to go ahead and use that point? We're going to plug it in. So the y would be -1 and the x would be 0. How do we know which root to use though? The positive or the negative? What do you think?
You have to use the negative because you can't have a negative answer.
You can't, a square root will never produce a negative answer. That's why it's always on the right-hand side of a graph. Another way you can kind of think about that is since the -1 value is negative, we need that negative square root. Okay, so we're going to use a negative root. Let's go ahead and solve for c. We can move the negative over. And then to get rid of a square root, we can just simply square both sides. So it looks like our c value is 1. So bringing it all together, We're going to take our general solution and simply plug in 1 for c. We said y would have to equal the negative square root of x squared plus 1. There's the exact equation of that curve we drew on our slope field. Okay, the equation that goes through that particular point. So there's kind of a free response type question. Drawing a slope field, I think we're good. Drawing an equation or drawing a curve, I think we're good. The hardest part is probably the working backwards, but it's a process, but they reward you for that process. Every little thing has a point to be earned. So just like we discussed last time, if you make a mistake, it's not the end of the world. Just carry it through and you should be fine. Okay? We're going to have more practice with these free response type questions tomorrow because we're going to have a free response day. But other than that, we're done with the section. What do you guys think about slope fields? Do you like them as much as I said you would?
Time consuming.
Time consuming but easy? Yeah, okay. I'll take that then.